Alright, so a scalar is just a number. It's an amount. It's a value. If we're talking about a speed or a number of pounds or a distance, we're talking about scalars. Okay, if I just say I was driving 45 miles an hour, all you know about what I was doing is the speed. You don't know where I was going or anything like that. Okay? Where a vector is different from a scalar is that a vector has both magnitude, which is the scalar portion of it, but along with that is direction. Okay? Direction. So when we're talking about velocity, a lot of people use velocity and speed interchangeably. It's really not accurate to do that. Okay? Because a velocity is a speed in a particular direction. I said I was driving 45 miles an hour north on Lyons Road. Now that's a velocity. You have a speed and you have a direction. Okay? A force is a direction. Alright? He was pushing down with 100 pounds of force. Okay? So pushing down, there's our direction. And we also have the magnitude, the number of pounds. We can also have displacements. Displacements are movement, okay, a model of movement. So in that case, we'll be given a direction and a magnitude. And that we've actually already dealt with when you guys looked at bearings. Okay, when you were given bearings, you were told that, you know, we were at this angle and we went this far. Okay? How far is our magnitude, and the bearing would have been the direction. Okay? Now in physics, a lot of the times you're given both of these. Okay? And you're often given those things because they're easy to measure. But when we're talking about putting vectors together in, say, a study of statics or dynamics, if you go on to study physics or engineering in college, you'll take probably an entire course on statics, which is just the physics of making things stand still, okay, or stay the same. And dynamics is the physics of making things move in different ways. All right, so when you're doing that, in order to study that, you need to take what you can measure in real life, which is typically the magnitude and direction. We know a certain number of pounds of force, we know what direction it's being pulled, but then we break that down into components. And we're gonna focus a lot of our study on components, which we'll talk about a little more as we go forward here. Okay. But that's what a vector is. Let's talk about some notation. Vectors are one area of mathematics where the notation varies quite a bit. There are a number of different ways to express vectors. Depending on what book you read or what part of the world you're from, you'll see it a lot of different ways. So I'm going to try to show you as many as I've seen, and I'm sure there probably are more out there. But let's take a look at the most common notation. First of all, if we're naming a vector, we can name it one of two ways, okay? First of all, you can name it with a lowercase letter with this little, notice it's like a half arrow above it. That's vector V. In your textbook, you might see it written in bold font, okay? You cannot handwrite bold font, so don't try. You guys need to put the little arrow above it, okay? But in textbooks or other printed work, you'll see it listed in bold font, okay? You may also see it, this is a lot more rare, I haven't seen this very much at all, but you may also see it with the lowercase letter with the little tilde above it. That's what that little squiggle is called, a tilde. So that could be the name of a vector. You could also name a vector based on the points that it starts at and it goes to. Okay? notice vector AB starts at A, and notice the arrow is going to B. Okay. Now, here's the thing that you have to be careful about. Just because it has an arrowhead on it doesn't mean it keeps going. This is different than geometry. In geometry, you had array. If you had array AB, it started at A, it went through B, and then it kept going forever. It was a half a line. A vector has a defined magnitude, like we said. So it goes from A to B and stops at B. However, we put the arrowhead on there because the direction matters. Okay? In this case, the order of the letters matters because A coming first means we started there and we're going towards B. Okay? So you do have to pay attention to that. There's a lot of notation that you've got to make sure you understand here right at the beginning, or otherwise, as we move forward looking at vectors, you're going to get confused really fast.
So
Okay?
the quantity from A to B would be V if it was like the same.
Well, we could call that vector AB, or we could assign another name V to it if we wanted. Now, we talked about magnitude. There are also two ways of indicating the magnitude. Your book uses this with the double lines. Okay. However, another acceptable, and I'd say probably a little more common, is just to have single vertical lines on either side. But there we're talking about the magnitude of the vectors. Okay. Your book does use the double one. I don't care which one you choose to use. They're both valid though. The reason why people will use the double vertical lines is to eliminate any confusion with absolute value. Okay, but if you understand absolute value is an operation on real numbers, these aren't numbers, these are vectors. Okay, so the absolute value of a vector doesn't really make sense. But anyways, you have both types of notation. Then we have these component vectors. This is what I said we were going to focus on more than you may have in your in a physics class. Okay, component vectors give a horizontal and vertical component of the vector rather than the explicit magnitude and direction. Okay, so for example, in physics, you may have had a problem where a guy was pulling on something at a 45-degree angle with 100 pounds of force. Okay. There, you're explicitly given the direction and magnitude. Okay? Here, you might be given that a guy was pulling on something, and he was, let's see, what would it have been? What did I say, 90 pounds of force? 100 pounds of force? Okay. So it would be 50 radical 2 pounds of force horizontally and 50 radical 2 pounds of force up. Okay?
So that narrows down at like 45?
That's the same thing as saying he pulled 100 pounds at a 45-degree angle, except what I did is I isolated the horizontal pull and the vertical pull as two separate components.
If you combine them, you'd get the 45 degree, right?
You would, yeah.
He's got like this, so if you found like pulling it as both at the same time, you'd get this.
We'll apply that. That'll make sense as you go forward, as we look at other applications. So
Yeah, I don't like it.
it's okay.
Yeah.
All
I
right.
don't have to like it.
Now, right now, all you need to do is understand the notation. I want you to see this notation right here at the beginning. Okay. You'll get over it. Okay. So here's one. Here's one way of showing a vector. You'll notice it looks an awful lot like a point. Okay. It's not a point though. It's a vector. Okay. It is given as an ordered pair. The first component is the horizontal component. The second component is the vertical component. Okay? Now, obviously, it would be really easy to confuse this with a point, so we have other forms of writing the same vector. One of those is to write them vertically like this. Okay? We have vector AB, but we write the two components up and down.
Isn't there something else we learned?
Matrices like that.
Yeah, there's 4 that we're going to look at. Oh, matrices, you can write this too.
But don't, like, what was it we looked at in chapter 8? The,
All combinations.
yeah,
Yes. There's
okay.
notation is used the same in a lot of different contexts, and that's why you have to pay attention to context. When you see notation, if I just gave you this and said, hey, what is that?
But that
You
could-
could say, oh, that's a vector, or you could say that's a combination, or you could say that's a 2x1 matrix, or I don't know what else you could call it, but you could call it a lot of different stuff. Okay?
That is
You
a
gotta
mental
fan drive.
breakdown.
Alright. Now another way that you can express this same vector is again going horizontally, but notice again to avoid confusion with the point, to avoid confusing it with a point, they use these arrowed brackets instead of parentheses. Okay?
I think that's the
I like that. Yeah, I like the second one. No, I like
So-
third one.
The third one.
Then you have the last one. Now, I will say your book uses this third one a lot, okay? As I've looked at it, the book uses that most often. I use this probably most often, but I'll mix it up just to keep things interesting. The last one
Interesting.
is a little less commonly used, however, it does have its application, and it actually has a name. It's the unit vector form, and that's where we actually have A times this vector I plus B times the vector J. And I and J are what are known as the unit vectors. Okay?
I don't like this one.
That's alright, you don't have to like it, you just have to recognize it. Okay?
Are you gonna give us
So,
quiz problem with that thing?
you should be able to recognize and use any of those notations.
What do you
What
mean?
are you use the next one?
What's I and J supposed to be?
The I and J we'll look at later. Those are called unit vectors. I is the horizontal unit vector and J is the vertical unit vector. Okay? We'll talk about those though later on. Okay?
No.
So, any questions so far?
Why?
Yeah. Alright. Now, I want to look at the different aspects of the vector a little more closely. First of all, the magnitude, okay? The magnitude of a vector. We've got these vectors over here, okay? The magnitude of a vector is represented by the length, okay? It's represented by the length. So as you're sketching things, all right, if you have 50 pounds of force and you have 25 pounds of force, then in your sketch you ought to make the 50-pound vector about twice as long as the 25-pound vector. Okay? We're representing things with a length that aren't lengths. Okay? The more you'll pay attention to that and try to draw things to scale, the easier problems will be for you. Okay? So just keep that in mind. Yeah.
Still confused. Is like a vector like an arrow that ends?
Yes. The arrowhead is just to show us which direction we're going. Because like this one up here, we could either be starting here and go up like this, or does it start up here and go like this? If all I had was a segment, I don't know which way I'm going. So that's what the arrow is for.
How do you express a vector?
How do you express a
How do you
vector?
express like the arrow? Like you know?
You just draw it like that. Draw a little arrowhead on one end or
And
the
like in
other.
equation form, you just put like 3 and the arrow on top.
Yeah.
Well, that's the thing. 3 would be a scalar, but you might have a v. Yeah, you could have 3 times v.
Just takes
All right.
it to us.
Just
You'll see. Okay? So, when we're talking about a magnitude, or just to kind of put it into words we've heard before, you could be talking about the speed of a velocity vector. That would be its magnitude, alright? You could be talking about the pounds of force. Okay? It's not enough to just say, 50 pounds, alright? To have a vector, it'd be 50 pounds in a certain direction, but the 50 is that magnitude. Okay? Or if we're talking about a displacement vector, it could be the distance of the displacement, alright? We are going at 45 degrees for 2 miles, alright? So the 2 miles is our magnitude, it's a distance. The direction we can actually liken to slope, okay? You can liken the direction to slope. Because we're in 2 dimensions, if you think about our component vector, it's talking about a horizontal shift and a vertical shift, right? You have a horizontal component and you have a vertical component, alright? So if I wanted to figure out a direction, then I could consider what slope that would be, okay? So if I have a vector AB, slope is rise over run, right? So what would the slope of that vector be?
B over A.
B over A, okay? The vertical component over the horizontal component, okay? Now, here's where slope and the direction are a little bit different, okay? The direction will be the same if you reduce the slope, but reducing that slope would change the magnitude,
So you can't reduce.
okay? Well, here's the thing. You can reduce as long as you recognize you're not dealing with a vector, okay? You're dealing with a scalar at that point, which is just a direction, okay?
Wait.
Just the magnitude.
No, it's not a magnitude.
Well, you said you did the scalar, which is just a direction.
Well, this is a scalar as well. A scalar is just any number.
So vectors are scalars, but scalars aren't. I mean, scalars are vectors, but vectors aren't.
No. It takes 2 scalars to make a vector, okay? Because you need a horizontal component and a vertical component. Remember, a scalar is just a number, alright? Now that number could be an angle, if it's talking about the direction. That number could be an actual magnitude, okay? But regardless, a scalar is just an angle. If I said I was traveling at a bearing of 50 degrees,
Scalar.
that's a scalar, because it has a direction, but it has no magnitude. How fast were you going, or how far did you go, or what more, I need more information in order to actually have a vector for your thing, yeah. Okay, so when we're talking about the direction, you can use slope to describe your direction, but understand, if you reduce that slope, you can't just translate that slope back into a vector. I guess that's what the kind of point of saying this is I can't take a slope, and if it says that my object is moving along a path with a slope of 2/3, my vector isn't necessarily 3, 2. It could be 6, 4, or 9, 6, okay? Because I might have reduced to get that slope, okay? So, slope and direction of a vector are related, okay, but they're not, you can't necessarily go back and forth between the two. Yes?
So if you have B over A, you cannot simplify that at all.
Well, I mean, you can simplify it, just understand that if you try to go back to write the vector, then you're not gonna get the same original vector, you're gonna get it the right direction, but it'll have a different magnitude. Okay? And actually, you see that right here. Notice this vector and this vector have the same direction, but they have a different magnitude. Okay? Now you'll notice this one right here has the opposite direction. Okay?
So it's A over B. And if the first one was B over A, that would be A over B? No.
It would actually be
Negative.
negative. Yeah.
Okay.
So negative A, negative B. But notice it would be the slope actually would be the same.
Yeah, it'd just be negative.
But it would be negative A and negative B, and then a negative divided by negative would be positive. Okay? So that's where it's a little bit tricky. And that actually does lead us to the next thing I want us to recognize, and that is, what do we say about things that have the same slope?
They're parallel.
They're parallel. So, obviously these are going the same direction, so they're parallel. What about something that's going the opposite direction?
Parallel as well.
It's parallel as well. So, in order for vectors to be parallel, they have to either go the same direction or opposite directions.
That kind of makes sense, like it's kind of like self-explanatory.
Yeah, and basically what it is you're looking at their path, not necessarily how they're moving, but their paths are parallel. Okay? So, all three of these, to use the notation from geometry, you know, when you put these little things on there that shows they're parallel, all three of those vectors would be parallel. Any questions? Comments? Anything? Okay. Now, this is different than two vectors being equivalent or being equal. Okay? In order for two vectors to be equal, they have to have the same direction and the same magnitude. Okay? So, it's possible to have two vectors with the same magnitude but different directions. Okay? It's possible to have two vectors with the same direction, same direction but different magnitudes. Okay? So you can have same magnitude, different directions. You can have same direction but different magnitudes. If you have the same of both, then those vectors are actually the same. Okay? So here these two vectors are the same. Okay? They're identical, they have the same direction, they're the same magnitude, so we would call them equivalent vectors. Yes?
Isn't the magnitude just like the value, like the length of the vector?
Yeah, it is represented by that length,
So-
yes.
Why wouldn't the vectors be equivalent if like they have the same magnitude, but one's going like up and one's going down? Because they're the same length. So why
Because
does
they
that
have different directions.
Yeah, but why does that matter? Because like they both end, you know? Like they have the same
Yeah.
length and they both end like, but he's going down and he's going up. Like,
So they're not the same.
But they still have the same length.
There's only one.
So they have equal magnitudes, but they're not equivalent vectors. Okay? In order to be equivalent
Sorry, Derek.
well think, in order to be equivalent vectors, they have to do exactly the
So they
same
have to be
thing.
identical.
They have to be identical.
So like
Okay.
they're okay.
Let me illustrate like this. I think this might help. Okay?
D represents disappointment.
Let's do this, okay? So here we have two people here. Okay.
D for disappointment.
We'll draw our people. Okay,
Yeah.
there we go. Oh, that's
really wrong.
way too big.
Is that Jacob?
There we go. Okay, so
Come on, that's
here's one person.
Smart.
come on, that's it.
and here's another person, okay? So, if those two guys are pulling, let's say they're both pulling on a rope, okay? And they're pulling, whoop, let's say they're pulling with equal vectors, okay?
What that means they're
Here's the rope, and it's going like this, okay? And it's tied to something over there. Okay.
Draw an elephant.
This work.
We'll,
Pull with
I
your
love
drop
summer
around.
board.
there we go.
My favorite game.
It's pulling that, all right? So now, here's what we have, okay? They're pulling with equal vectors. That means, come on,
I'm not even pulling, it's just you pulling yourself against me.
and this is why the direction matters. Oh, come on.
I'll just take Derek's word for it.
That's bigger than the
Why will it not
direct these guys?
Wait, what is that? Derek, he didn't do anything.
Yeah, he was like, he got freaking mad.
Derek
He was like, it's just one of the components. Sorry.
All right, there we go. Okay.
I'm not as math as you.
So here we go. Here's this guy's vector, okay?
Is it really worth it?
Listen, I know we're taking a little bit with this, but listen, okay? Here we have equal vectors, so that means we're pulling together, right?
Yes.
If we had opposite vectors, okay? If we had opposite vectors, we're not pulling the box together. What are we doing?
Pulling against each other.
We're pulling against each other.
Unless one of them is stronger. No, but the
And there's a whole nother thing, okay?
because the vectors are the same length. So
What are we doing if we're pulling with opposite vectors?
The equal are against each other.
canceling, like it'll cancel.
Well, are the vectors the same magnitude?
What do you need to subtract?
Yeah.
Yeah, they're still the same magnitude, but they have the different direction.
Then they're,
So what are these guys doing?
they're
They're
canceling.
pulling against each other.
Yeah, they're pulling against each other, so we're doing a tug of war here. Okay?
Oh, that's
They're pulling against each other, and assuming the magnitudes are the same, it's going to be a tie, right? No one's going to move anywhere. The opposite directions means that we're not going anywhere. Here, with the same direction, these are equivalent. Here, we have the same magnitude,
different direction.
but opposite directions.
You good?
He's calling that. He's out of it.
Okay?
Ask if I look cool.
Now, actually what we just looked at is a good introduction to the next thing I want to see here, and that is operations with vectors, okay? You'll notice here we have different vectors that are being put together, okay? And anytime we're dealing with something new in mathematics, we have to consider different operations with them, all right? When we had complex numbers, you couldn't just add everything up together. We had to redefine how to add complex numbers. You add the real parts and you add the imaginary parts. That's how you add two complex numbers. Well, here, when we're dealing with vectors, we have to consider a similar thing, okay? So,
What is it?
let's say that we have these two vectors here, u and v, okay?
What were you?
Yeah, I remember something.
And what we're going to look at is adding two vectors together and then also multiplying a vector by a scalar. These are the two operations we're going to start with here today. Alright, so when we're adding vectors, and we're looking at adding vectors geometrically or graphically, first of all, these are like following directions, okay? If someone gives you directions to go somewhere, you don't do step 1, then go back to the beginning, and then do step 2, right?
Why do they use
I mean, if I tell you, walk a mile north and then 2 miles east, you don't walk a mile north, then go back to where you started and then walk 2 miles east, do you? You do 1, and then wherever you left off, then you do the next one. Well, that's how vector addition works. If I want to do u plus v, I pick a starting point, so I started right here, and I travel u, and that again could be a velocity, it could be a displacement, it could be a force, but then I need to add to it v. So from the end of u, I add v. Okay, that's like the second step in our directions.
So it's like direction.
It's like directions, okay? So what's happening here, the result, which we call the resultant vector, okay? The result, u plus v, goes from the point where you started to the point where you ended, okay? If you ever travel anywhere, if you're looking at a map, you're doing this all the time. Because you can rarely go in a straight line from where you are to where you want to go. You have to go down this street, then over on this street, maybe up another street. Okay? The end result is you went from here to there. Okay? You just didn't see all the steps in between. The resultant vector is like the straight line that you draw from your starting point to your ending point. Okay?
Is it called resolute?
Resultant vector, yes. That's the term for that, is the resultant vector.
So that's a straight line from wherever you start to where it ends.
Yeah, from where you start to where you end.
Connect the dots.
Yep. Okay? Now, one question someone asked in third period was, well, what if you did V first and then you did U? Would you end up getting the same place?
No. Yes. Maybe. I don't know.
Well, let's see, okay? So, let's say I start at the same place and I go U first, or V first, sorry. Then, from the end, I go along U. You'll notice we end in the same spot,
Oh, cool.
okay?
So
Sorry, what?
doesn't matter the order.
The order doesn't matter, which is what in addition?
The additive property?
It is an additive property, but
Cumulative
not
property.
associative. Commutative
Commutative.
property. It's the commutative property.
It's just the
So
camel
guess what?
property.
Now we know for vectors the commutative property works. We've known it works since elementary school for adding and subtracting numbers, or adding numbers. Okay, now we know it works for adding vectors. The order doesn't matter. And by the way, look at this. This is why this method of adding, we call it the head to tail method. Alright? Because the head of the second one goes on the tail of the first one. Okay? Or sometimes it's also called the parallelogram method, which you can see why that is. If you do it both ways, you get a parallelogram. Okay? Now you don't need to know the names of those two methods, but that's why it's called that. Okay? So, relatively simple concept. Sometimes though it's a challenge to express things in terms of different vectors, which we'll practice later. The last thing I want to look at here is scalar multiplication. Alright, I'm going to say, well, multiplying two numbers together. That's easy, we've been doing that since second grade. We're not talking about multiplying two scalars, we're talking about multiplying a vector by a scalar. Okay? A vector by a scalar. So in this case here, let's say we have 3u. Okay? if I have 3u, that's the same as taking u plus u plus u. Okay. Now, let's look at what happens when we do that. Here are 3 u's. I added them together. Okay? But you'll notice 2 things happen. Number 1, the direction stays the same, and it just forms a longer vector in that same direction. But also the magnitude gets multiplied. If I'm trying to find the magnitude of 3u, and I know what the magnitude of u is, I can just multiply that magnitude by 3. I don't have to find the magnitude of the new one. I just multiply the magnitude of the original vector by 3. Okay? Yes? You know, can you hang on for like 4 minutes just while we close up? Alright. So, if you think about it, this makes sense. Alright, let's go back to the illustration of 2 guys pulling on the same box. Okay? If they're both pulling with a vector u, okay, then how much of a vector are they pulling with when you put them together? 2u. Okay? So if one person, if they're both able to pull with, 150 pounds of force, then when they pull together, now you have 300 pounds of force. Okay?
So it's, you really add them.
You're adding, well, it's 150 times 2.
So it's like
Pulleys are a little bit different.
Pulleys is,
There's mechanical advantage.
So they-
Now, part of what you're thinking about, though, actually, if you have a pulley up here and it's tied, actually, I shouldn't say a pulley up there, but say whatever you have, your rope is tied up here, and then it goes down through a pulley, and you're lifting from up here, okay? The reason why your mechanical advantage is doubled is because you're lifting at a certain vector, but the ceiling or whatever this is tied to is also holding up that same amount of weight. Okay? By tying it to this, you're actually doubling your vector as you pull it up. Okay? But there you have basically 2, you're using the ceiling to help yourself out. Okay? But that's 2 times the vector. Alright guys, we'll see ya. Have a good day.